Hello, it's Ryan. This is our last example on forces. I wrote it out. A crate full of fruit is let go from rest on an inclined plane. The coefficients of friction between the crate and the incline are mu sub k, the coefficient of kinetic friction, 0.6, and mu sub s, the coefficient of static friction, 0.9. In general, the coefficient of static friction is almost always higher than the coefficient of kinetic friction. There's only a few rare surfaces that's not true. So in general, that's something you could just kind of keep as a fact, I guess. We're going to determine the maximum angle that the incline can be for the crate to remain at rest. So for the crate to remain being impacted only by static friction. Then we're going to determine the angle, given that the angle is 1 degree higher, what the velocity of the crate after it slides 3 meters down the incline will be. So this is a two-parter. We're going to start this problem like any other problem by drawing a picture. And so here's our incline at some angle theta. Now, someone might look at this and say, no, that's a decline. An incline is a decline. It all depends on where you're standing. If you're standing where our crate is, then you might be tempted to say that this is a decline. But if you're standing down at the bottom, you would be more tempted to say that it is an incline. Anyway, there's our crate, and it's going to go some displacement, s, down the incline. And so it'll end up down here, and it will have some velocity. And we just might call that VC for velocity of crate. We also know that its initial velocity is 0. And we could also note that this surface here, there's a mu sub k or s on that surface. And so we could do our knowns and unknowns. We know the mass of our crate. Well, that was 31 kilograms. We know mu sub s and mu sub k. We know s is 3 meters. We don't know theta. We don't know the acceleration, and I could label the acceleration of the crate down on our picture. Isn't it going to accelerate down the incline like so? But that would only be when we're beyond theta max. So we could put theta max. And so the idea is this. If you have a crate on an incline, if we could just change the incline, there's going to be a certain theta that the coefficient of static friction and thus the force of static friction won't be strong enough to hold the crate anymore, and it will start sliding down. So we're going to try to determine where that happens. So what we need to do is do an FBD for the crate. And this is going to be while the crate is stationary. So this is an FBD for the stationary crate. And being stationary means the surface of the crate and the surface of the incline aren't moving relative to each other. And the reason I say that is because we'll know that it has static friction opposing the potential for motion on the crate. So there's our crate. I drew the crate on the angle that the incline is at, just to kind of match the picture. Now I'm going to draw in some forces. We know the crate has a weight force acting on it. We know the crate has a normal force, and it's normal to the surface, so it's on an angle as well. We know that the crate will have a friction force opposing the potential for motion, and so it will be holding the crate in place. We also know for this stationary crate, A is 0. Now we need to choose a coordinate system for this FBD. And really, we kind of have two somewhat obvious choices. We could create our coordinate system, a regular XY coordinate system. But if we do that, we'll have to we'll have to show the components of our normal force and our friction force. So to try to save us some time, and you should do this in the future for yourselves to save yourselves some time, the mindset or the goal is to try to break up as few vectors as possible. And so all I have to do is create my xy plane on the same angle as the incline. And now my normal force will only be in the y direction, and my friction force will only be in the x direction. And so I will have to show the components of only one force, the weight force. So I can break the weight force into its y and x components. Now, in order to tilt this crate at the same angle as the incline, we would have to be tilting this downward vector the same angle as the incline. And so we have our theta right there. So this is a good free body diagram. Anytime we do a free body diagram, we should sum the forces in the x and y directions. But before we move on, I just want to show that for this triangle here, we could do the trig. We know the sine of the angle is equal to, in this case, sine is opposite, which is weight x over weight. And so something to remember, weight is always mg. And so weight x is mg sine theta. And if we did cosine of the angle, we would see that that gives us weight y over weight. So mg cosine theta is weight y. Now, all I did was, once we drew our triangle, I wrote out these expressions in case we need them. Okay, so using our free body diagram, I want to sum the forces in the x direction and sum the forces in the y direction. And we're just going to use our free body diagram to do that. Looking at the FBD, it looks like we have 2 forces in the x direction. And in my coordinate system, I made to the right positive, so we'll have weight x positive minus friction, and it's static friction because the crate's stationary. And we said A is 0, so that equals 0. Well, that means I can replace weight x with mg sine theta, and we always know that the friction force is always the coefficient of friction times the normal force. So I'm going to just rewrite these. mg sine theta minus mu sub s times the normal force equals 0. And I'm just going to go ahead and do the same thing for my y direction. In the y direction, we have a normal force going up, normal, and a weight in the y going down, minus weight y, and a is still 0. So this tells us that normal is equal to mg cosine theta. So I can substitute this in here, and we can solve for theta as the problem asks. So we'll have mg sine theta minus mu sub s mg cosine theta equals 0. Okay, so here's a little trick for you. What I would do is I would divide everything by cosine. 0 divided by cosine theta is just 0. Cosine theta divided by cosine theta is 1. And sine theta divided by cosine theta is tangent theta. We could also divide everything by mg because these terms have mg in them. So these all turn to 1. And 0 over mg is 0. So we'll be left with something much easier to solve. This will give us tangent theta equals mu sub s, right? These are 1. These are 1, and we're left with minus mu sub s. So if I add it to the other side, I'll get this expression. So if we do the inverse tangent of both sides, we can answer the question, or at least the first part of the question. So if you calculate this with your calculator, you'll get 42 degrees. So this would be the maximum angle where the static friction force can maintain the crate's position on that incline. The next part asks us to add 1 degree to that, so we'll say if theta is 43 degrees, now we have to do a new free body diagram, and it's gonna feel very similar to the old free body diagram. So this will be an FBD, but now it's a sliding crate. So here's our crate. It will have its weight and its normal force acting on it still. It will have friction opposing its motion, and it will be accelerating down the incline. So we'll have the friction force still, but now because it's moving, this will be kinetic friction. And we should also show that it is accelerating down the incline. So it certainly looks very similar to the previous problem, except now it has an acceleration and a kinetic friction. So we'll tilt our coordinate system so that we can keep our A in only one direction, and our weight will be the only thing that we have to split up into its components. Weight y, weight x, theta, same thing as the last one. So now we can sum the forces again, only this time we have an acceleration in our x direction. So the sum of the forces in the x direction equals ma. We can't get rid of the a. So now we have weight in the x minus kinetic friction equals ma. We could rewrite this mg sine theta minus mu sub k times the normal force equals ma. Those are just the identities of those equations, and of course the trig from our weight triangle. AY is 0 because the A is down the incline, and we call down the incline our x direction. And so the y direction forces are, again, the normal minus the weight in the y. And that's equal to 0, so we still get that normal as mg cosine theta. And now we can input this into our normal force again. So we have mg sine theta minus mu sub k mg cosine theta equals ma. We can divide the m by everything, and they'll turn to 1. And we could factor a g out just to save typing in our calculators. But there it is. If we were to go ahead and substitute our values in, we could get that number, but we don't really have to. I'm just going to go ahead and continue on with the problem. It didn't actually ask for A, it asked for the velocity at a certain displacement. Once we have this expression for A, what we're really looking at now is a kinematic problem where we have a crate moving some displacement of 3 meters, and it's accelerating that way. So this has actually just become a kinematic problem. It looks to me like this equation might be the easiest one to use because we were given delta S, V sub O, and we now know A, so we could solve for the V after a specific displacement, right? So we can say V equals the square root of 2A delta S, because V sub O is 0. V equals the square root of 2 times, and we're going to put in A, G times, and it's this, sine theta minus mu sub K cosine theta times the 3 meters. And if we go ahead and type this all out, we could give the velocity of the crate after 3 meters of motion, and it would be 3.78 meters per second, and we will say down the incline, just to make sure we show the direction. So that was a pretty good problem.